You've got me in a stranglehold, baby. You've given me the RV fever. Let me bug on out of here.
Hello YouTube, this video is going to be about planning your battery. And I'm going to turn this over to my assistant here, and he's going to tell you all about batteries. First, we're going to determine the power needs. There is a website by Wholesale Solar that has a load evaluation calculator. Let's navigate to that calculator. If you'll click the link down below the video, it'll take you to the Wholesale Solar site, and if you scroll down the page, you'll find the load evaluation calculator. On the left hand side, it has a place for appliances. You'll list all your appliances here. If you type in these spots, it'll give you a list of items to select from. Keep in mind they don't always provide the exact watts that your particular appliance will use. Look on the manufacturing tag, and or you can plug it into a watt meter and it'll tell you how many watts per hour it uses. Put that number in the watts column, and then you're going to need to figure your hours per day usage. Refrigerators don't typically run 24 hours a day. Mine runs 15 minutes every 24 hours. So I multiply 15 times 24. Then I'll convert that back to hours by dividing by 60. And I'll get 6 hours. So every day, my air-refrigerator burns 300 watts. The other big draw in my van is the microwave. It is a 1,000-watt microwave, and I use it typically 3 minutes in the morning, 3 minutes at lunch, and 3 minutes for dinner. And I'll round up to 10 minutes. So 10 minutes calculates to be, I'll take 10 divided by 60 minutes, and we'll say I'm going to just put 0.15 hours, and that's 150 watts. Now, my biggest draw, I think, is my induction stovetop. There is not one listed here, so I'm just going to type it in. And just one of them. And it draws, at the level I run it at, it draws 560 watts. And I use that about an hour a day. It's 20 minutes in the morning, 20 minutes at lunch, and 20 minutes at dinner. And I really don't use it that long, but that's what I'm going to calculate at. So that's 1 hour. So that's 560 watts. And I have a laptop, phones, multiple, and iPad. And I do use those quite a bit. I usually charge them for about an hour a day. And they burn about 250 watts. But I'm going to put 2 hours a day because sometimes I do use them more than others. And that gives me a total of 1,510 watts. Now I'm going to round that down for simplicity, but that's how I got my total watt usage. You can do it however you like, but this is an easy tool to use. Okay, so we've already figured our daily usage. We need to calculate our total storage need. And that's very simple. Just take the figure you just got. In my case, it's 1,500 watts. Multiply it by the number of days of storage you want available, and that will give your total storage need. Mine calculates out to be 4,500. However, I am going to build a 5,000 watt storage battery. So we've got the total storage. Now we need to do the battery design. Now you get to select the voltage of your battery. You get to decide the voltage of the system. What inverter will you be using? If you've already got an inverter that's 12 volt, of course you'll probably want to build a 12 volt system. If you haven't purchased anything, I'd probably try to persuade you to go a little bit higher. And the same with your charge controller. If you've already got solar panels and a charge controller, then you would want to build your battery to meet the requirements of that particular equipment. Cost is important. 24 volt is always more money than your 12 volt systems. And also it's determined by the amount of power you want to invert. If you get a 1,000 watt inverter or less, a 12 volt system works fine. However, if you got appliance that needs more than 1,000 and you go to a 2,000 watt inverter, then I would definitely consider using a 24 volt system. My battery needs to store 4,500. As I said, I'll be building a 5,000 watt system. And back to the physics equation, volts times amps equals watts. So that I know a 24 volt nominal battery, so I know the volts, and I know the size I want to build, then I just got to solve for the amp hours. Solve the equation for the amps. You just take 5,000 divided by your volts, and this is the amp hour that you've got to build. Now I'm going to run that down to 200 amps. So each of my 18650 batteries test above 2,000 milliamps or 2 amps. So to determine the number of batteries we will connect in parallel, we'll take the amp hours we need and divide by the average capacity of each of your cells. In my case, that would be 2,000 amp hours divided by 2 amps. That's what each of my batteries tested at, which means I need 100 of the 18650 cells in parallel. And how do you do that? Well, you have to build a holder, and this holder holds exactly 100 cells, 5 deep by 20 long, and these are positive. You can tell they're positive by the white protectors on the front of them. All of these batteries are wired together and come out on this one post as the positive side, and on the other side is done the same way with the negative. So if I were to put a meter across here, it would read 3.7 nominal, but this right here holds 200 amp hours. 18650 batteries have a nominal voltage of 3.7 volts. When they are fully discharged, they are 3 volt. This varies with each brand of cell. Some discharge values they'll give you at 2.75. I always use 3. I would never go below 3. And when fully charged, they have 4.2 volts. So when I connect 100 18650 batteries together, I have one cell that is 3.7 volt nominal with 200 amp hour capacity. Now, I was going to give you some term information. Parallel means that the voltage stays the same. So no matter how many batteries you connect in parallel, the voltage stays the same, but the amperage adds up. So 100 batteries at 2 amps is 200 amp hours. Now series, you put more than one of these big cells together, then you add the voltage and the amps stay the same. Nominal voltage is determined typically by your battery manufacturer, and that's what we'll all use for the nominal calculations. Now we need to determine how many of the cells we need to use to get to the voltage our battery needs to be. For example, if you wanted a 24 volt battery, you can divide 24 volts by the nominal 3.7, and that equals 6.4 cells. You should notice that you cannot have 6.4 cells because all cells have to be equal. You can't have one cell being 100 batteries and another one being 130 batteries. All of them have to be the same. So we can either build a 6-cell battery or we could build a 7-cell battery. I typically always will round up from this number, and that's what I have done. A 7-cell battery is 3.7 nominal times 7 cells is 25.9 volts nominal. Now let's look at both of these batteries we could have built. The 6-cell battery would be 6 cells at 3.7, which is 6 times 7 is 22.2 volts nominal. But more importantly, we need to look at the voltage at maximum charge, and this would be the 4.2 times 6, which equals 25.2, and look at the fully discharged rate, which is 3 volts times 6 cells is 18 volts. This would not work with my 24 volt inverter. Note, you need to take a look at your inverter data sheet and see what its voltage range is. Now my Xantrex 24 volt sine wave inverter DC input range is 20 volts to 32 volts. So the 6-cell would not work because the discharge rate is 18 volts. Remember, we calculated the 6-cell discharge voltage to be 18 volts, so that won't work. This is my inverter. It is much more expensive than you see the Chinese inverters. These inverters were typically used in the marine industry and still are, and your very quality RVs. Now, notice I didn't say expensive RVs. Expensive has nothing to do with the equipment that's in an RV. Typically, if you want a quality RV, you have to have it built and specify the electronics you want in it. Xantrex is the top of the line. They are quite pricey, but as you see from the data sheet, my DC voltage range input is 20 to 32 volts. So I need to build a battery that fits these parameters. Now let's look at a 7-cell. 7 cells at 3.7 volts equals 25.9 volt nominal. Fully charged, it's at 29.4. Discharged, it's at 21. Notice that 21 is above the minimum and 29.4 is below the maximum. That is what is important. This inverter allows me to set a minimum voltage, so if I do not want my battery to get below 25 volts, I can set it to shut off at whatever voltage I want. Now, one thing about this inverter, it is a multiple inverter. It has a fast switch, so as soon as I connect to shore power, it disconnects my battery, and then it checks the voltage of the battery. If the battery is below full value, the charger kicks on and charges up. But it puts the AC from the shore all the way through to all of my outlets in the van, so it's not using the battery at all, and does this automatically. Additionally, this inverter can connect to a generator, and I can set a minimum voltage on my battery. If I'm not connected to shore power, it will actually start the generator and supply the power in the van and charge my battery back up. I do not use that function. I do not have a generator in my RV, and I don't think I ever will for many reasons, and I'll go over those later. So next we need to determine the total number of cells to meet our storage needs, and we determined that our storage needs was a 5 kilowatt battery. So I have determined I will build a 7-cell battery with 100 batteries in each cell. So 7 times 100 equals 700 batteries. So I need to crack open over 700 batteries, test them, and then I can actually put this battery together. Now let's discuss battery terminology. You will see many batteries made for skateboards, hoverboards, and electric bikes. The new 750 watt bike batteries are listed as 14S 5P 52 volt battery, Well, what does that mean? It means the battery that we will be building is a 7S 100P battery. 100 batteries per cell, 7 cells in series. That's what the 7S and the 100P. So when you see that, you won't be confused on batteries that are out there for purchase. That's pretty simple. So the total capacity is the nominal voltage times each cell's capacity. So in our battery, we have the total capacity of each cell we're building is 100 cells times 2 amps per cell is 200 times the nominal voltage of 25.9 volts, which equals 5,180 watts. And my goal was a 5 kilowatt. I'm just a little bit over that. And that's how you figure your total wattage that you're storing. And the last thing we just need to verify that our battery we're building meets the draw, amperage draw designed for these batteries. And the way we'll do that is we need to calculate the discharge rate. This is the maximum amp draw from our battery running the most watt hungry item in our RV. In my case, the microwave is the most demanding. This is also important when picking an inverter. If the inverter is rated for 1,000 watts, I would buy a bigger inverter than 1,000 watts. Standard engineering practice is to build 20% more than your maximum load. The reason for this is when you first start a device such as a microwave, it pulls more power to get started. This is more true with electric motors. They can pull as much as 200%. An air conditioner that runs at 1,000 watts sometimes can pull 2,200 watts just to get the motor running, the compressor running, and then it will drop down to its running watts. So that's something you need to be aware of. So how many amps for your most power hungry device demand? In my case, again, the microwave pulls 1,000 watts from an AC outlet. I actually verified this by plugging into a watt meter and watched for a minute or two. When it first started, for the first 3 seconds, it read 1,200 watts, then dropped down to 950 watts. To determine the number of amps the battery will have to provide to be inverted from 24 volt DC to 120 AC, we need to do some more math. The same equation, volts times amps equals watts. In fact, my inverter tells me how many amps it's pulling from the battery. But to calculate it, we'll take the battery size, which is 24 volts, times amps equals 1,000 watts. And we'll solve for the amps. So we'll take 1,000 watts divided by 24 volts, and that means 42 amps. So the largest draw on this battery running the microwave will be 42 amps. This is a lot of amps, and you do not want to get between that and the ground, or it can kill you. Volts do not kill, amps do. 42 amps is very reasonable. Now, if this was a 24 volt system, you would double that. You would be pulling 84 amps. But if you're using the same number of batteries, 84 amps is still below the rating, as you'll soon see. So does our 24 volt battery meet the amperage demand? Let's calculate. Before we can calculate, we need to look at the manufacturer's data sheet for the batteries we're using for our build. Since our battery is 100P and each cell is rated at 4 amps, 4 amp draw, we can multiply the 100 cells by 4 amps to determine our maximum amp draw. We can safely discharge 400 amps. Note, I would never do that, but when Tesla Model S is at full throttle, it's pulling over 900 amps. So we're pulling 42 amps from 100 cells. That equals 0.42 amps per cell. That is well below the 4 amps it can supply safely. Now, all you have to do is on the batteries that you have, type the code that's on the battery. Either it's LG battery or Sony battery. These are Samsung batteries I have. And I was lucky. I only have 2 different kinds of batteries. The last battery that failed on me, I had many different kinds of batteries. But this battery has got 86%. I've got 560 of this kind, and I've got 240 of these batteries. So if you scroll down the data sheet, you will see, and what you're looking for is, what's important here is the discharge current. And these are rated at 4,400 milliamps or 4.4 amps. Remember, we calculated we're only going to be drawing 0.4 amps, not 4.4. And this sheet's also going to be important when you go to charging. One thing to note, a lot of these data sheets will be rated in C rather than giving you the actual amperage. And I used to have trouble with, what the hell does this C mean? It's very simple. After many hours of search, I found that C just is your capacity. So this battery would be rated discharge at 2C. It's charged at 1C. And these other batteries, you'll note, and the reason you want to compare your batteries, you want everything to be pretty much the same. And one thing else that's important about these data sheets, for example, all the batteries I'm testing, I'm only putting batteries above 2,000 milliamps in my battery, and they're all testing between 2,000 milliamps to 24. Well, you say, how can they be 24? Well, these are the minimums. This is the minimum. They'll ship these brand new. And the normal capacity that you'll normally get out of the new batteries are 22. Mine are rating are testing almost new. And they're all the same. And notice that both of this is the 22E, this is the 22F. And what surprised me about looking at these two data sheets is the weight. This battery is at 48 grams, whereas this battery is only 44 grams, but they got the same characteristics. This tells me the chemistry in this battery is different than the chemistry in this battery. But all of the data is equal, so these batteries are compatible to put in one battery, and that's important. Well, that is how you do it. Took a little bit longer than I'd hoped. Hope you stuck with me. Sorry it took so long. But until next time, check you later.